Hello and welcome to Varsity Eco. Today we are going to continue with the second order condition with our Cobb-Douglas function example. So before we start, I must say that in our undergraduate days, initially we used to say the students that find out the second order condition and check the border Hessian, it is mandatory, so on and so forth. But eventually, after some months or so, we always tell them that just write down the SOC is satisfied. Now, the point is that with Cobb-Douglas, in some cases, checking is necessary, but in some other cases, it doesn't matter. So today, after the derivation of the border Hessian, we will look into that aspect also. Okay, functions or structure of Cobb-Douglas, where you can just look and directly say, okay, the second order condition is satisfied. So the general structure is the Lagrangian was like this. Okay, x1, x2, and our specific example was a into x1 to the power alpha into x2 to the power beta plus lambda into m minus p1 x1 minus p2 x2 lambda greater than 0. Now, in general terms, if we say the border Hessian looks like this: 0, p1, p2, p1, p2, scriptal xx, scriptal xy, scriptal yx, scriptal yy. So these p1, p2s, they make basically the border. This function is, this part actually is typically the Hessian determinant. Now, again, if we write from FOC, we know that xx equal to 0, which implies that, or if we start with that, Lx equal to 0, that is will be del scriptal, or according to our notation, it should be x1, x2, or we can directly write 1, 2, 1, 1, 1, 2, 2, 1 and 2, 2. Okay, so L1 equal to 0, that is del scriptal del x1 equal to 0, which basically implies that u1 minus lambda p1 equal to 0, that is u1 equal to lambda p1. Okay, fine with that. Now, if we differentiate this structure, then L11 is simply u11, and this lambda p1, if differentiated once del x1, it will be 0. And this structure or this result will be applicable to all of them, by which I mean that scriptal 1, 2 will be u12, scriptal 2, 1 will be u21, and scriptal 2, 2 will be u22. Okay. So when we will be solving the problem, we will not write this version of border Hessian. Instead, we will write this version: 0, p1, p2, p1, p2, u11, u12, u21, u22. So what does it mean? It means that if I have to check only the border Hessian determinant, then I don't need to construct this Lagrangian at all, or I don't have to look at this. Okay, so let us find out these four values. Taking from here, u1 a into alpha, x1 to the power alpha minus 1 into x to the power beta, which means u11 is alpha into alpha minus 1, x1 alpha minus 2, x2 to the power beta, u12 is a alpha beta, x1 alpha minus 1, x2 beta minus 1, then u2 is a x1 to the power alpha beta, x2 to the power beta minus 1, which means u21 is a alpha beta, x1 to the power alpha minus 1, x2 to the power beta minus 1, U22 is A beta into beta minus 1 into x1 to the power alpha into x to the power beta minus 2. So from here we can directly see the basic result, that is U12 equal to U21. So ordered Hessian is 0, P1, P2, P1, P2, A, alpha, alpha minus 1, x1 to the power alpha minus 2, x2 to the power beta. Okay, here A, alpha, beta, x1, alpha minus 1, x2, beta minus 1. We set P2 here. So again, the same term. Here U22, so A, beta, beta minus 1, x1 to the power alpha, x to the power beta minus 2. Alright. So if you open minus P1 into P1 into A beta minus 1 x1 to the power alpha x to the power beta minus 2 minus P2 A alpha beta x1 to the power alpha minus 1 x to the power beta minus 1 plus P2 into P1 alpha beta A into alpha beta x1 alpha minus 1 x to the power beta minus 1 minus P2 into A into alpha minus 1 into x1 to the power alpha minus 2 into x2 to the power beta. Alright. Now if we okay, so minus P1 square A beta minus 1 x1 to the power alpha x to the power beta minus 2 plus P1 P2 A alpha beta x1 alpha minus 1 into x2 beta minus 1 plus this same term again. So we can directly write a 2 here, which is the exact same term. Then this is gone, so minus P2 square A alpha minus 1 x1 alpha minus 2 into x to the power beta. Now to help ourselves, what you can do is we can take this negative sign out and make this 1 minus beta. So if we go by that, P1 square A beta 1 minus beta x1 to the power alpha x to the power beta minus 2 plus P2 square A alpha 1 minus alpha x1 to the power alpha minus 2 x2 to the power beta plus 2 P1 P2 A alpha beta x1 to the power alpha minus 1 x2 to the power beta minus 1. Okay. So SOC for maximization. The leading principal minors must alternate in sign starting with a negative sign. Okay. Now in bordered Hessian, this first term here is 0. So that is why when we count the leading principal minors, we don't consider this one. If we write H1, then that essentially means 0, P1, P1, and let's write U11. Now this one, whatever U11 is minus P1 square. So by default this is negative. So it starts with a negative sign, and first one is trivially negative. So this border Hessian, complete border Hessian here, which we otherwise also say H2, this has to be positive. Okay. Now let us look at this expression. In this expression, if alpha and beta both are either less or equal to 1, then this border Hessian is positive always. If we put beta and alpha equal to 1, then they will become 0, and this one is positive here. And that happens because initially we have said that alpha and beta both are positive. Okay, so the only case where you have to actually test is when alpha and beta they are greater than 1, because in that case this here will become negative, this also here will become negative, and in that case we are not sure whether the sum will be positive or negative, or for that matter 0. But if these two are less than or equal to 1, then we are quite sure that the second order condition is satisfied. Now let us first summarize the result. So the result will go like this. Given u equal to a into x1 to the power alpha, x2 to the power beta, with a, alpha, beta positive, h2, that is our complete border Hessian, so to say, for this function is strictly greater than 0 for alpha, beta less than equal to 1 always. However, with alpha comma beta greater than 1, we need to check for optimal x1 star comma x2 star whether border Hessian is positive or otherwise. So that means, to start with, or from the point where you started, that if we are writing that SOC is automatically satisfied, then that line can be written if this is true. But in this case, it may not hold. There is another trick which is in the bag, and the trick goes like this. If u equal to a into x1 square, x2 square, then alpha comma beta both greater than 1. So you may think that, okay, what to do? We have to check putting x1 star, x2 star, but that is not needed at all. Why? Because then just consider an increasing transformation like this, v equal to u to the power half, which is a into x1 x2, and here dv du is half into u to the power minus half, which is positive. So for positive x1 x2 values you don't have any problem, and because these are 1, here also you can write SOC is automatically satisfied. And when SOC is automatically satisfied, you have a huge advantage. So here what we are doing is that here we are using the trick of increasing transformation along with our first result here. But there is only one catch, and that catch is use it only when alpha equal to beta, because if alpha beta are uneven, then we have a little bit of problem. For example, if u equal to a into x1 square x2 to the power 5, then we have real problems. In that case, we need to actually evaluate the border Hessian. But then, so here is our setup. U equal to a into x1 x2, where alpha and beta are both 1. P1, P2, 2 and 1, money income is 10. Here alpha equal to 2 and beta equal to 5. We are going to show what happens to the border Hessian using numericals. Okay, so for this one, let us find out the border Hessian first. So that will be, it is too easy. So 2, 1, 2, 1. Then U1 is A x2 and U11 is 0. U12 is A, which is U21, and U22, okay, U2 is equal to A x1, so U22 is equal to 0. So that means 0, A, 0, and as you can see that this leading principal minor H1 is minus 4, so that is negative. Now the bigger one, so minus 2 with 0 minus A, last one with 2A. So 2A plus 2A equal to 4A, which is positive because A is by structure positive. Now one point that we'll come to that. Now what about this one? This one's border Hessian will be, so 0, again 2, 1, 2, 1. Okay, so U1 is A 2x1 x to the power 5. So U11 will be 2A x2 to the power 5. U12 will be 2A x1 into 5 x to the power 4. So that means 10A x1 x to the power 4. U2 is A x1 square 5 x to the power 4. So U21 is equal to 2A x1 into 5 x to the power 4, which is exactly equal to U12. So we are correct. U22 is A x1 square, then 20 x2 cube. So let us write like this: 20 A x1 square x2 cube. Okay. So if we put them here, so 2A x2 to the power 5, then 2A, let's write it like this: 10A x1 x to the power 4. This is identical. And the last one, 20A x1 square x2 cube. Okay. So minus 2, so 40A x1 square x2 cube minus 10A x1 x2 to the power 4 plus 20A x1 x2 to the power 4 minus 2A x2 to the power 5. Okay. So technically speaking, if we do not know the x1 star x2 star here in the second case, if we do not know x1 star x2 star, we cannot comment on this value. So we need x1 star x2 star to find out h, and this is what creates the difference. This one, where we do not need, in this one, we do not need x1 star, x2 star, which means that it doesn't matter, right? This function has a maximum and it is not dependent on what we got in the first order condition. But if we have to find out, we can find out by the shortcut, that is 2 into x1 star divided by 10 will be half. So x1 star will be 2.5, right? And again x2 star by 10 will be half. So x2 star will be 5. But we don't need these two numbers to put in here. We know that this is positive and this is negative. So this one is a case of global optimum. Okay. So this Cobb-Douglas has a global optimum at these 2 points. Whereas for this one, without having x1 star, x2 star, I cannot really comment on the sign. So let us find out them. So how will it be? 2x1 by 10 equal to 2 by 7. So that will be x1 star equal to 10 by 7, and then x2 star by 10 will be equal to 5 by 7. So x2 star will be 50 by 7. So we have to put these values here and find out whether the value of this one is positive or not. So do it at your home and tell me what do you get, whether it is positive or negative. The important learning here is that if in this problem you write SOC is automatically satisfied, we are good. But if in this problem you write second order condition is automatically satisfied, then you are wrong. It is not automatically satisfied. It depended on the value that you have got here. Okay.